Hi again, Calculus. It's Mrs. Jurosik, bringing you 8.3, Separable Differential Equations. I'm going to kind of cut to the chase on this one and get us started right away. This is basically going to be a video on the types of problems we haven't been able to do yet because another method or process needs to happen in order for us to solve this type of differential equation. Okay, so this is the last section in chapter 8 that we will actually be going through before we start unit 8, according to AP again, chapter 6 for us. Okay, so separable differential equations. So we've done slope fields so far. We have solved, I guess, basic differential equations. Notice that there were only really x's in those equations or just y's, not really both at the same time. When we dealt with slope fields, we did graph a few things that had both x's and y's. We didn't necessarily go about solving them though, okay? So let's put this all together in section 8.3. So sketching solutions of differential equation using its slope field is a powerful technique, and it proves a wealth of information about the solutions. However valuable as they are, slope fields do not produce the actual solutions of a differential equation. In this section, we examine methods that lead to the solutions of certain differential equations in terms of an algebraic expression, often called an analytical solution. The equations we consider are first order and belong to a class called separable equations. So I have 4 examples of what separable differential equations may look like. And notice what's a common theme. There is a y value in all of them. And then the other thing to notice is that they are all products or quotients. So basically what we're talking about here is easily separable. There are certain types of equations that have x's and y's in them that we would not be able to use the process on. They are not actually separable. So like if you had an x plus y equation, we can actually not use this process for that. So there is definitely that theme of 2 of these expressions either being multiplied or divided with each other. Okay. So part A, or the first one in A, dy dx equals ay. A is a constant. Okay, so this one only has the y value in it, the y variable. Okay. So we're going to start basic and we're going to move our way through a few more complicated problems. How do we solve the differential equation dy dx equals ay? The dependent variable, not the independent variable, is now on the right side with no obvious independent variable to be found. So just as a recap, right? Y being the dependent, X being the independent, okay? Basic anti-differentiation will not work, so we need to separate the variables. So your procedure, okay? So I'm going to take you through dy dx equals ay. We're going to solve that one using a process that we want to use moving forward when we're using the separable method, okay? All right, we're going to separate the variables. Generally, or I should say, I 100% of the time put the y on the left, okay? I'm never going to say I put it on the right, okay? So your y's are going to go on the left, x is on the right, and constants go to the right. So that would mean the a has to stay on the right side. So what I have right here is just a series of steps showing us we start with that. And we are going to dy stays on the left, and we have ay dx. And then what we have is we divide both sides by the y, bringing the y to the left side. And then the a, the constant, stays on the right. So I have an asterisk, set of 3 asterisks, just noting something. We are not multiplying by dx, but the resulting notation would imply that we did. We're moving it, we're separating the variables. It's not an actual operation of multiplication, okay? Not that you need to know any of that. It's just keep that in the back of your mind. It's not actually multiplying by it, okay? We are simply at the stage of separation, okay? All right, the next move we need to make is we need to integrate the left side with respect to y and the right side with respect to x. So what's more important than anything in this step is going from this in proper notation to what is to follow. So what we want to do is we actually want to write with integral symbols our problem. We're taking the antiderivative. This is the separation step. And why I'm pointing this out is because when it comes to grading your problems, these are the key things your graders are going to look for. Your separation of the variables, as well as taking the antiderivative of both sides. So that's putting the symbols on it and not just going straight to what the antiderivative is. Okay, so if I take the antiderivative of 1 over y, we've done lots of practice at this point, I'm going to go directly to ln absolute value of y. And the antiderivative of a is a times x, right? Dx. Not dx, excuse me, ax. Instead of saying dx, I meant to say plus c, right? So this is important because with the plus c, I took an antiderivative on this side, which would also mean, and I'm going to do this in a bright color to make it stand out, I would technically have plus c on that side as well. The reason, because I'm about to erase my pink plus c, is because make note of this. Both integrations produce an arbitrary constant of integration that may be combined into one arbitrary constant, which means the one that we combine it into is the one on the right side. So moving forward, I won't be putting the plus c on the left side at all. This plus c right here has absorbed all the constants for right now, okay? All right, now we need to solve this for y. That's the point of all of this. If you're solving it for y, you have to do some algebraic techniques, pre-calc techniques here. Ln absolute value of y is not y equals. So we would want to exponentiate both sides. So when I do that, I'll spell it out just so we are, right? That's exponentiating both sides. E to the ln of anything is the anything. Does everybody agree? So we have y equals, and when I do this, I'm going to talk about the absolute value in just a second. E to the ax, e to the anything, does everybody agree, is always going to be a positive value. So I would be able to actually do that right now. Okay, we should be good to go. And e to the ax plus c, here's some algebra, some good refresher algebra. I'm going to rewrite this as that. Just think for a second what your rules of exponents say. If you have the same base raised to an exponent and you go to multiply, you would then just add your exponents. I'm doing that in reverse. And moreover, what I'm about to do with this, e to the c, e is a number, c is representing a constant, another number. We don't know it. So what we're going to do is we are going to make this into one arbitrary constant called capital C. Okay, so y is equal to, and it comes out front, right? It's going to be multiplied in front, c e to the ax. All right. That is, I'm not saying the easiest example to start with, but a very good example to start with, because sometimes the ones that require logs and or taking integrals, when you have then roots involved, and when I say that, square roots or anything of that sort, sometimes those get a little bit more complicated. So I definitely wanted to walk you through one of these because this is typical of something that you may have to actually do on your AP exam. Okay, so I have another small note at the bottom here. Two things. The last bullet, because this didn't apply to the particular problem I did, if an initial condition is given, you would use it to evaluate the arbitrary constant. So if they gave us an initial condition on this of, it goes through 0, 1, right? What is the C value? So you would plug in like we did in section 8.1 and then in turn 8.2 with certain problems, and we'd get our C. And then this last note, if you need to take a square root or an even root of y, so your setup would look like, right, like this. So like y squared equals x squared plus 3x plus c or something like that. And you would be doing this. You have to make sure you've got that, right? You'll need to leave the plus minus in front of the answer, especially if it's just a general solution, unless an initial condition is given. So let's say the initial condition was you go through 0, -1, and you need the y value to turn out negative. Well, then you'd be picking the negative answer to that. If it was going through initial condition of 0, 2 instead, then you'd want to pick the positive of the two. Okay, so I just want to make note of that. We will get to examples like that. Just wanted to bring that up because it is going to appear. Okay. All right, so we're just going to dig right in and we're going to start practicing. So basically what we're doing is we're adding steps, different types of problems, but we're just adding a couple of steps in here. And let's practice. All right. Find the solution of dy dx equals e to the negative y times sine x, subject to the three different initial conditions. All right, here we go. Notice, first of all, why is it separable? Because I have the term sine x multiplied by e to the negative y. I can easily undo them by a process of either division or multiplication. Okay, so here we go. Step 1, separate my variables. So set the problem up for what you need to do. So that means the e to the negative y, you divide by e to the negative y. All right, so if I do that, and that's on the left side, and I'm going to put the dx on the right side with sine x. I'm separated, right? I'm going to do one more step, and I'm going to make my 1 over e to the negative y is e to the y. So right there, if you could have jumped to that first, this move right away, fine. If you didn't see it, it's okay if it takes you 2 steps to do it. Now I take the antiderivative of both sides. We show this step. We can't just jump to the antiderivative because then mathematically that does not make sense in your steps. Okay, you have to put the antiderivative symbol. Okay, here we go. Antiderivative of e to the y is e to the y. Antiderivative of sine x is negative cosine x plus c. Remember, our arbitrary constant is all of those wrapped up into one. All right. I'm trying to get this into y form, right? So y equals form. So let's go ahead, instead of exponentiating both sides, in order to get my unknown exponent to move in front, if you will, I take the log, natural log of both sides. I like leading with a positive when I have a natural log or a log expression. That's just me and my preference. If you wrote it inside as negative cosine x plus c, it's perfectly fine. So my simplification then is that. All right, I've got my y equals form of this. I've got 3 different problems, 3 different initial conditions. So I'm going to take it through one at a time. All right, so for A, 1 is equal to, so I'm starting out with y equals, let's do A, y equals ln of c minus cosine x. All right, let's plug in. 1 equals natural log of c minus cosine of 0. 1 equals the natural log of c minus 1. Okay, so that's not a good c value, right? We need c equals. Well, then we're exponentiating, right? E to the 1 equals e to the ln of c minus 1, which then just means e is equal to C minus 1. All right. So that's our C value. A little weird, right? E plus 1, but that's a number. It's 2 point whatever, whatever, whatever plus 1. So 3 point whatever, whatever, whatever. So final answer for A. E plus 1 minus cosine x, right? I'm taking out C and I'm plugging in E plus 1. Okay, that's A. All right, let's go for B. Maybe after I do B, you could pause and you could try. Okay, B. So let's go with B. If we start out with y equals ln of c minus cosine x, B is y of pi over 2 is equal to 1/2. So my y value is 1/2. Natural log of c minus cosine of pi over 2. Cosine of pi over 2 is 0, right? Again, right? If you exponentiate, c is e to the 1/2. So y equals ln of e to the 1/2 minus cosine x for B. All right, if you want to pause, I'm going to start going through my very last one. Okay, so let's go C, y equals ln of cosine, C minus cosine x. So -3 is my y value, ln of c minus cosine of 0. So -3 equals ln of c minus 1. So again, exponentiating both sides, e to the -3 equals c minus 1. So e to the -3 plus 1 is c. So my final answer for C would be y equals natural log of e to the -3 plus 1 minus cosine x. Okay. All right. Next example. Find a function that satisfies the following initial value problem. dy dx equals y squared times e to the -t. Initial condition is y of 0 is equal to 1/2, and t has to be greater than or equal to 0. Okay, so again, separable because two terms being multiplied together. One has the y, one has the t. We're not mixing and matching. We're not doing plus and minus things. We can easily multiply or divide to move things around. So let's go ahead and do that. Picking colors, for some reason today, seems to be challenging. I don't know why it is challenging, but it is. Okay, here we go. Again, separate is our first move. So if I divide both sides by y squared, and I leave e to the -t and bring my d of dt over, that is what I'm starting with. Okay. Now, when I take the antiderivative of both sides, showing my proper notation, I will end up with I'm going to go right side first only because negative e to the negative t plus c, right? That's that. And then 1 over y squared, remember, is y to the negative 2. So this would be negative y to the negative 1. Okay. So it's up to you if you want to rewrite it as negative 1 over y, if that's easier, or if you just think about something, if I want to make this y equals, if I were to take both sides to the negative 1, I'm going to get, I would do, before that, would I multiply through? Maybe I'll do this first as opposed to that. Sorry. Just change the order of what I'm thinking through. If I were to multiply through by negative to make it positive y to the negative 1. Does everybody agree with that? A little bit nicer, and then raise everything to the negative 1. How's that? Okay, so that's my y equals. As not pretty as it is, it doesn't matter. And I have my initial condition of 0, comma 1/2. So I'm going to go ahead and start trying to find my c. So I've got 1 minus c, right? So this would be, so I've got 1/2 equals 1 over 1 minus c. 1 minus c equals 2. C is negative 1. Okay. And I can rewrite my final equation with c plugged in. Okay, so we are ready to just declare that as y, and we are good to go. In any of these, you should be able to take your derivative of what you end up with, and with maybe some manipulation, you should end up with whatever your differential equation was to start. Okay. I'm trying to make this video a tiny bit shorter than the other one, so let's keep going. These are the last 3 problems. I will get through all of them, but let's see how we do. All right, if you're feeling good, maybe pause, try a couple, and then, put the video back on. So what I wanted to do, so dy dx equals 2y. So there's no x at all, but remember what we said from the beginning. If there's a constant, you leave it on the right side. So let's go with 1 over y dy, and we have 2 dx. 1 over y dy, taking my antiderivative of both sides. Natural log absolute value of y, equals 2x plus c. Okay. So again, natural log y. What am I going to do here? Probably want to exponentiate both sides, if you will. It's also going to be positive here. So again, since you did this, which is the key. So from this step right here, before I exponentiated, that is key. Okay. And I'm going to actually leave my absolute value on here only because when I go to do something in the final steps, because look at my initial condition, if you will. something that I want to point out in a couple minutes. Okay, so give me just a couple seconds, I should say, and we'll get through this. 2x, and I'm separating. Remember, I'm going to do this only for the net for like maybe this problem, and if it comes up again, I may skip over this step. You don't have to show all of this, but remember what this means when you're undoing that exponent property. It brings this out front, right? And the reason I'm going to trail this absolute value down is because when I'm plugging in to solve for C, if you think about that, absolute value means the positive and the negative of whatever you're doing, right? It's plus or minus. So when I take this off, it's kind of like that thought of we're not sure what we're doing yet. So I'm going to put that in a little sort of offset that. So with that, -1, right? -1 is CE to the 0 power. So -1 equals C. So with that being said, once I plug in, you can write your final equation as negative, you don't have to put the 1, right? Negative e to the 2x is your final answer. Okay, my initial condition was negative. On these types of problems, it is not as important to do that. You don't have to show the plus minus in front, but please make sure with your initial condition that once you're done with your problem, with these natural log problems, you make sure that if I were to plug in 0, right? If I'm plugging in 0 right here, negative e to the 0 is 1, so negative or opposite of that will give me -1. You just want to make sure that when you're plugging in that x value, you're going to get the y value that matches the initial condition y value. Okay. All right. So maybe pause again if you're feeling good and try it. So my separation is 1 over y again. Oh, look at that, another natural log. Right? So putting on my integral symbols. All right, natural log absolute value of y. And this would be x cubed over 3 plus x plus c. Okay, so e to the natural log y. So same thing. I'm going to leave off the absolute. I'm going to just kind of, we know that this is technically always a positive situation. So if I leave it off this time, let's just do this. So we don't have to think that we have to dwell on that all the time. E to the x cubed over x cubed over 3, excuse me, plus x. And then we've got the plus c. Is everybody okay if I don't do times e to the c? I can just bring that in front. So what I actually should have done, I wish I'd left myself a tiny bit of room. Okay, so that was that. And now for my initial condition, if I plug in 4 equals CE to the 0 cubed over 3 plus 0, that's going to be e to the 0, which is 1. So 4 is my c value. Which I do at that, which I just for good measure. Okay. So my final answer is y equals 4e to the x cubed over 3 plus x. And if you go back and look and I plug in a 0, I will get 4 as my y value. Okay. All right. So I definitely want you to pause, try this one. I'm actually going to do the same. And when you come back, you'll see the answer. Okay, we're back. So this one, again, right, separable because a y term multiplied by a term with an x in it, easily undone by using multiplication or division. And initial condition of 3 comma 1/4, okay? So separating gives me 1 over y squared and 6 minus 2x dx. And I got to this same situation I had in the previous problem to this one, where you end up, after you take the antiderivative of both sides, negative y to the negative 1. So I did the same thing I did before. I multiplied through by the negative, and then I raised everything to the negative 1 power. So I have my y equals form. And then it's just a matter of plugging in 1/4 and 3, or 3 comma 1/4, and solving. I ended up with a c value of negative 13, and the final equation being y equals 1 over x squared minus 6x plus 13, because the minus and negative will cancel into a positive. Okay. One minor thing, or one thing I would like to say about just these problems in general. Once you've taken the antiderivative of both sides, you do have the option. So once you're at this, oh, that's not what I wanted to say. I want to be on my pointer. Once you're at that stage, and I've taken the antiderivative, you are technically free to solve for c whenever you wish. As we practice in class and you practice on your own, you may find that you want to solve for c at a different time. Whenever possible, if it's easy to get it to a y equals form, then solve for c. I prefer that. And if there is a time where it starts to get very confusing to solve for y first, and maybe it's just I want to get my c value now, that could also be the case. So the one type of problem that we did not go over yet, which I may just throw one in here real quick, is the square root style of problem. Okay, so we'll put one more on our notes packet. Okay, so I've added a problem here where we may get, a square root example in there as well. All right, here we go. So moving things around, y dy equals x plus 1 dx. Antiderivative of both sides gives us y squared over 2 equals x squared over 2 plus x plus c. So I've got that divided by 2 thing going on. So we could actually solve for c right now. This is what I was talking about. If you want, you could go ahead and plug in c right now. You could manipulate the equation a tiny bit before you do. But here's something I want to show you. If I were to just multiply through by 2, so everybody see that? Yes, you normally multiply everything through by 2. It's an arbitrary constant. If you didn't multiply through by 2 on the c value only, remember, 2 times a number is still a number. You could leave it as just c, okay? So let's keep going and let's plug in. Maybe we'll show it both ways. Let's go ahead and leave it the way it is, and we'll finish the problem off. So notice what's about to happen. If I want to solve this all the way for y right now, I have the c, this 2c is going to be underneath the radical, right? Maybe what I want to do right now is actually plug in the 0 comma negative 2 and see what happens. Okay, so let's do that. So I've got negative 2 squared equals 0 squared plus 2 times 0 plus 2 times c, which would give me 4 equals 2c. C is 2. Okay. All right. And now I have to take from this stage, I'd go y squared equals x squared plus 2x plus 2 times 2, which is 4. And now I'm ready to do that. Plus or minus. Now I'm looking at my initial condition. If I need to get -2 as my answer, the only way that's going to happen is if I take the negative or the opposite of the square root. So my final answer. Okay. So whether you do the problem exactly the way I did it there, or you left C as just C and not 2C, should end up with the same answer. So go ahead and give it a try. Okay, I'm going to pause for a second. So what I'm saying is maybe try it with just C instead of making it a 2C. Okay. Okay. So all I wanted to prove was that you get the same exact answer. If I hadn't taken the 2 and applied it to the C itself, meaning I rolled it into one arbitrary constant. Notice what happens. I still plug in to solve for C. This time instead, I get a C value of 4. So I'm like directly there. Okay. And so it's in there. But bottom line is you end up with the same exact answer. Okay. All right. Now we are done. And hopefully this will at least get you to a good place for when you practice in class and then start your 8.3 homework. All right. Thanks for your attention, everybody. I'll see you in class. Bye-bye.